Okay, so um, this problem is about finding smallest all ones multiple. So you're given a positive integer k, and we need to find the smallest integer n that is divisible by k, and consists of only the digit 1 in its decimal representation. So 1, 1, 1, 1, 1, 1. And we return an integer, which is the number of digits in n, and if no n exists, return -1. Okay, that makes sense. So let's say that k is equal to some integer, 2, 3. It could be any integer. And we need to find the smallest digit, 1, 1, comprised of only ones, such that it is divisible by k. And so basically mod k is equal to 0. Now the easiest way to do this is, let's just take some integer k. Let's say k is equal to 3. And let's just start with 1. Let's call our number 1. Is it divisible by 3? No. So we can just add another 1. Is this divisible by 3? No. So we add another 1. Is 1, 1, 1 divisible by 3? Yes, it is. So we can now return the number of digits in 1, 1, 1, which is 3. And it's that simple. But the problem is that the number 1, 1, the number here, it could be much larger than any integer long can hold. So it could be very large. Let's say it's like 30 digits. There's no variable that can hold this number. So now, what we must do in order to be able to successfully hold this large number is, we take this number 1 and we mod it by k. So we need to do some modular arithmetic. And this is okay because any number that that is a multiple of this modulo is also divisible by k. What I mean is, let's say 1 mod k, or let's say 1 is not divisible by k, neither will its modulo, right? Now let's say 11 is not divisible by k, neither will its modulo. And let's say 1, 1, 1 is not divisible by k, neither will 11's modulo times 10 plus 1. So we can perform the same operation on this number and we'll basically get whatever this modulo is. Okay, so yeah, you can try this out on your own, but basically the modulo of the previous remainder, if we do the same transformation on it, it will give us the same remainder as if we had transformed the original number right here. Okay, so now that we know this, what we can do is we can take this number, we can start it at 1, then each time we, like, how would you turn 1 into 11? So you would multiply by 10 and add 1. So we do that to get 11, and before anything else, we also mod it by k. So let's say k is 3 here. Then 11 mod 3 is what? 2. So and we do the same transformation, but except we start it here. So 2 times 10 plus 1 is equal to 21, and mod k is 0. And like last time, the answer is correct. It took us 3 steps, right? So we can count the number of steps. This is step 1, 1 digit, 2 digits, and 3 digits. Now, here's some important edge cases. So if k is ever mod 2, or k is mod 5, we always return -1, because any number of ones cannot be even or end in 5 or 0. So now, one last step, right? So if we have this thing where we're multiplying the number times 10 and adding 1 to it, and then modding it by k, how do we know when to stop? This could be an infinite loop, right? And the steps keep going, but some numbers, they'll never hit, they'll never be divisible by k, no matter how many ones you can add. So we know when to stop because of the pigeonhole principle. So basically, let's take 3. So 3 has 3 possible remainders. So any number k has k remainders. So 3 would have 0, 1, 2, 4 would have 0, 1, 2, 3, right? So this would be size equals k, right? So now we know that at the most we only have to take k steps, because let's say we start at 0, and then some transformation takes us to 1, and then that transformation takes us to 2. Any more transformations, like 2 can only go back to any other point in this loop, right? So let's say you have a number like 5 that can never reach, that can never be divisible by k, no matter how many ones you add. So it will be 0, 1, 2, 3, 4. And it can start at, let's say, 1, and then 11 mod 5 is 1 again. So this is just a cycle that continues on 1. And for different numbers, it's different, the cycle. But the point is, at the most, we only need to run k steps. Alright, so now let's try coding this up. Okay, so let's do our first check. If k mod 2 equals 0, or k mod 5 equals 0, we know that the answer is wrong. Now, k mod 2 is equal to 0, or k mod 5 is equal to 0, answer is wrong. Now let's create an integer for the number and start it at 1, and then we can create an integer for count and start it at 1. So this is just how many digits there will be. So now for int I is equal to 0, I is less than k, and I plus plus. So we'll run at most k times. We also know that 1 will never be the number that we're trying to divide k by, because k starts at 2, and so any k and 1 mod any k will always be 1, so we don't need to have to check that. So let's start by transforming this number. We'll multiply it by 10 and add 1 to it. And we can also increment count because we're adding a digit. And now let's check if this number, oh yeah, and also let's mod it by k. So now let's check if this number is equal to 0. If so, we can return the count. And if after k iterations we're not able to return the count, we can just simply return -1. Yep, that works.